gravitational fields. Here we go. You guys found this in the notes? Okay, so long distance influences. The concept of a field was invented to explain action at a distance. How does the Earth exert a force on the moon without even touching it? Well, it has a gravitational field. So fields are invisible. You can't go out to space and try to find the field. You can't. It's just not there. We invented it. It's a mathematical tool that explains these interactions very well. And we talked a little bit on Friday about how, like, modern physics will talk about space-time and general relativity given to us by Einstein. That's the modern view, but in Physics 20 and Physics 30, you'll just be talking about gravitational fields, and they're a really good model. Like, they'll talk about fields absolutely at the university level. This is kind of a picture of the gravitational field in a sense. What do you notice about the field lines really close to the Earth? What do you notice about them all? Sort of all closer, bunched up, there's more of them. Compared to the moon where they're more spread out, there's less of them. So what would you ascertain about drawing the field lines? What would you suggest? The stronger the gravitational field, the more lines you would need. So would you assume the moon would have a stronger gravitational field than, pardon me, the Earth would have a stronger gravitational field than the moon? Yeah, because it's larger, it has more mass, and that's just a natural thing to assume. And of course, it's drawn with more of these field lines. In Physics 30 and Science 30, those courses, you're expected to be able to sketch and recognize field patterns, especially for electric and magnetic fields. Physics 20 is sort of a bit of an introduction, so you've seen it once before, and it's not brand new in the 30 level. So this is the formula for the gravitational field strength. You've already seen this formula before, have you not? What is this formula? This is just Fg, right? Bring the m to the other side, and what do you have? Fg equals mg. So we've been using this formula. And what is our value for g every single time? Every single time it's, we've been using 9.81. And we've been using a meter per second square in our discussions. But this is only for if you're on planet Earth, and this is only if you're on the surface of planet Earth. And this is only an approximation, because depending where you are on the surface of Earth, it might be 9.82, it might be 9.80, it might be 9.79. So it's an approximation. Usually they, if you do research on your own, if you look on Google, if you check, it's always 9.8, but the Alberta curriculum has got us using 9.81 all the time. So if you wanted to find little g, for, like, say maybe you were exploring planet Venus and wanting to check out that beautiful place, you would have to find g for the planet Venus. Well, how would you do that? Okay, so g is special to whatever mass is producing the gravitational field. Now if you look at the units, F, that of course is Newton, and mass, of course, is a kilogram. So you could change Newton to the standard units, and it would cancel out. You'd get meters per second square. But it's also nice to think about it as a Newton per kilo, as a force per unit mass. Force per unit mass. So what amount of force is going to be on a unit of mass? That is G. That is G. How much force per unit of the mass? So I'll open up this applet for you guys. Just gotta minimize this. All right. So this is not a picture of a gravitational field. This is something else, but it's pretty cool. It's kind of like a sinkhole. You can see these particles. Watch the particles as they come from the edge. You know, what happens as it gets closer to this like giant sink? They start to go faster, yeah. So what do you think the force is? As you're farther away, the force is smaller, and as you get closer to the sink, the big mass that's causing the warping of space, what's happening to these particles? More force, so they have more acceleration. That's only for a 1 over r. That's a 1 over r relation. We are used to the 1 over r squared. So it happens even, whoa, happens even faster. And then I'm just going to change the, so this is another way of looking at it. Think of like this yellow circle or sphere, because it's like in a three-dimensional view here, as a source mass. And it's the same idea. The particles are moving slowly far away, and then they speed up as they get in. I'm going to change the display from particles to the field vectors. So this is sort of a field diagram. What do you notice about all the arrows? Which way do they point? Towards the center of the mass. Yeah, and that's basically all you need to know about this. Is if, say, we were talking about the Earth, we would draw all our field vectors. You could sketch this one in your notes if you like. And it doesn't have to be perfect. They should be similar, but you just have to draw all the field vectors, the force vectors, inward towards the center of mass. That's pretty much really all you need to know. Is this one cool? I thought this one was pretty cool too. Sort of like when you're really close to the mass, you can see it's really concentrated. These rings, I would imagine as like a three-dimensional ring around the circle, around the sphere, and you can see they're really bunched up and concentrated near the object. And then as you spread out, and of course, if you look at my mouse cursor, I'm covering it up right now, but that says 1 over r squared. So as you get farther away, the force or these field strength vectors get weaker. So like if you double the distance, if you double r, what's going to happen to the g? What do you think? Quarter g. We talked about that, and that was in the quiz yesterday, right? What if you triple r? So now you're even farther away. It would be not 9 times, but 1/9, right? 1/9 as strong. So if you're really close, it's quite strong, but as you get farther away, they start to weaken by a factor of r squared. So and then think of it the inverse. If you double the distance, it's a quarter of the gravitational field strength. Well, what if you half the distance? Double the gravitational field strength. So if you get closer, the gravitational field strength goes up. If you get farther, gravitational field strength goes down. If you get closer, gravitational field strength goes up. Oh, sorry, my bad. That's awful. Thank you, sir. My bad. All right. So good talk. Let's go back to the lesson. All right. So this formula depends on the force of gravity of a test object and the mass of that test object. So I would say, like, you think about this if you were like super powerful, you're this omnipotent being, you have the Earth, and what you could do is you could be like, I'm going to put an asteroid right here. And then you drop it in there, and then what happens to that asteroid? Could you measure the force, and do you know the mass? You could calculate little g. Now for us, what we're typically going to be doing, I'll skip ahead. Go to this slide here. Is this one in your notes? We take the two formulas that we're comfortable with, and we'll do a little substitution. So you can put the word substitution here. Okay, so we know that little g is equal to Fg over m. We know that one. So what we're going to do is we're going to substitute Fg here, this capital Fg, with the other Newton's universal law of gravitation. We're going to sub this into Fg, this one right here. The gm1 m2 over r squared, we're going to substitute right there. Now look what happens in the math. This mass will cancel with this mass here. Okay? So let's think about like if we were doing the Earth and the Moon, and the force between those two. Then we would be interested in the gravitational field strength of the mass of the Moon, because the Moon, the mass of the Moon would be the test object. This is the test object, and we're going to see, because the Earth is much more massive, we would assume that the Earth is the source of this gravitational field. So then you have the mass of the Moon and the mass of the Earth in this formula. So then which one of those will cancel out? The Moon, Earth on the top, and then you have the Moon on the bottom. So it's the mass of the Moon that's canceling out in these two formulas with the substitution. And you get this formula down here in the corner, which is capital G, the mass of the Earth, and the distance between them squared in the bottom. So another way I like to think about this formula, I would cross out this E and I would just put source. That's what I would put here. This would be the formula to calculate gravitational field strength. Gravitational field strength. So remember in those applets I showed you, remember that giant sinkhole where all those particles were getting sucked into? So that's the source mass. The Earth is so massive, it actually bends space and time so that other objects that are smaller, as they get close to it, they actually get sucked into the Earth. And we can calculate the gravitational field strength at any point in space if you know this object's mass and the distance. So maybe the asteroid's here. I know the mass of Earth, and I can calculate this distance. Okay, well maybe I drop a space shuttle over here. I know the mass of the Earth. I know this distance. I could calculate the field vector. Well, it's basically just a point in space, and then I can calculate the gravitational field vector, G. So G is a field vector. What do I mean field vector? Well, we know what vectors are. They have size and direction. Well, a field is just a whole bunch of them. Does that make sense? A field is just a whole bunch of these vectors. Yeah, at the exact same radius, sure. And then what happens if I get closer? What's going to happen to this? What happens to this arrow? It gets larger because it's closer, right? So then, if I was to just drop a marble right there, which way is that marble going to go? It's going to follow the lines. If I drop a marble over here, which way it's going to go? It's going to follow the lines. If I drop a marble over here, where is it going to go? It's going to follow the lines. And that's how fields work. And this is the formula to calculate a single field vector, a single one. Okay, let's back up a couple slides. Mr. Spaceman. Oh yeah. Okay, the spaceman here. He's got 60 kilogram mass and experiences a force of gravity of 589 newtons on the Earth's surface. Determine gravitational field strength. What is gravitational field strength? Little g. Okay? This one's tough for students because you get used to the, maybe if you could put that away, that'd be great, Maria. We get used to the other formula. We get used to that gm1 m2 over r squared. Okay, that's Newton's universal law of gravitation. This little g is gravitational field strength. So sometimes when you're studying, you kind of get lost in the mix. If you're asked for field strength, you're asking for little g. Gravitational field strength, little g. So it's the force divided by the mass. This one's very straightforward. 589 newtons divided by 60 kilograms. And we get 9.82 newtons per kilogram. Calculate the gravitational field strength on the surface of the Earth. And then we'll do 1,000 kilometers outside the Earth's surface and see the relationship. Okay, boys? All right. So for the Earth, you're going to use the radius of the Earth. And this time we use this formula here, capital G, mass source, divided by distance squared. If you were in an exam situation, you would be able to find these two values on your data sheet, on the back of the data sheet. Okay, they're given to us here, so we can calculate 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24, and divided by the radius of Earth, which is 6.37 times 10 to the 6, and don't forget to square it. And I get a 9.83 newtons per kilo. This looks good to me. Now what about 1,000 kilometers for an orbit? What if you're way out here? What would be the gravitational field strength due to the Earth? Well, what are we going to have to do? Take the radius of the Earth and then add it to this distance I'll call A. The reason I call it A is because like in other similar questions, they call that the altitude. So that's why I'll call it A. So when you do a separate calculation, G, mass source, just use the radius of Earth plus the altitude, square that. I'll give that a second and then I'll show you how to punch that into the calculator. Okay, let's put this in the calculator. Okay, 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24, divided by, now here's the hard part. You're going to divide it by the radius, not the radius, but the distance between the center of the masses. So put a bracket, because we're going to have to do an addition first. So what's the radius of Earth? 6.37 times 10 to the 6 meters. Now we have to add 1,000 kilometers, because it's not just the radius of Earth. You're 1,000 kilometers above the surface. So how do you add 1,000 kilometers? Well, it has to be in meters. So 1,000 kilometers would be 1,000 times 10 to the 3, an extra 3 zeros. And you can't forget to square it. Okay? That's why I looked at that last question. Remember we calculated 0? That made no sense. So we had the wrong force value in there. The force on the International Space Station would be much higher. I was just using the force on Mr. Spaceman there. So what do you notice about the G value? It's still pretty close to 9.8. It's just a little bit smaller. Okay? So I don't want that last question where the one we scratched out to confuse you. It's not 0 out there. Like that one was only 400 kilometers away from Earth. 400 kilometers away from Earth, you're still going to feel the effects of the Earth. The Earth is so massive compared to 400 kilometers, right? So it was a little bit misleading that we calculated 0. Okay? So you guys okay with the 7.34? Sure. Yep.
Why can't we use the why can't we find FG first and then we use the G equals FG over M?
You could. You could.
You could?
It's the same formula.
I just used it only I'm only like two numbers off.
Yeah.
I got 9.81.
Mm-hmm.
And we got like 9.82.
So we use those two formulas to derive the new one. That's like what you're doing. It's the exact same.
I can do that on
Yeah. Yeah, you can. This is... well, you're probably only off because you rounded somewhere.
I didn't
Alright. You guys okay with that? Okay. So what value do we get? 7 point... Help me out. What was it? 7.34. Newtons per kilogram. Okay, this one here, this is a black hole, 15 times larger than the sun. So any calculation that we would do here would be of just an approximation, because when you have such massive objects, relativity will play a role here, and whatever calculation that you do on this, it'll be an approximation. It's good enough to get the point across. You're more than welcome to try this one on your own, but what would your weight be on this black hole? If you've done any sort of reading on black holes, if you know anything about them, like if you get close to a black hole, basically your particles of your body just get like they call it like spaghettified. Like you get like first your leg will go and then it's like it's so massive. Okay, think about like this water bottle. This water bottle is not very heavy, right? I could throw it pretty high up in the air, right? Could I give it enough velocity that it would leave Earth? No, it took human beings thousands of years to figure out that technology, to send like a rocket to space, right? Well, black holes are so massive that the fastest thing in the universe, light, which can get around the Earth in like what, 8 seconds or something, it can't even, light can't even escape the black hole. It's so massive. The, you know, escape velocity? Light isn't even fast enough to get away from this black hole. That's of course why it's called the black hole. We're too far away from our black hole. Most, like our galaxy, like the Milky Way, is likely orbiting a supermassive black hole. So we orbit the sun, like our galaxy orbits a black hole. All right, so this one here, we've been talking about gravitational field strength. Yep. On the event horizon. On the event horizon? That's what it's called. Hey? On the surface of it, so like on the edge of it. Yeah, just use 44. Okay, guys, we got to do this one. Okay, let's do this one, guys, and then you'll be done with these notes. Okay, so if you look at this example here, you have like a scaled, it's not a great picture, but you got the Earth, you got the Moon, and then along some line that connects their center of masses, some point P. This is just some point P. What would the gravitational field strength be at that point P? Well, the Earth would make this point P want to point to the left, but the Moon would want to make this point P point to the right. So then this is an example of a net gravitational field strength. So just like you would do in those other questions like you started the class with, just calculate them separately and then do a net calculation. So at this point, like, we're basically getting new stuff, but it's really not new in a way. So you would want to calculate G for the point P using capital G, mass of the Earth, divided by, what's the distance for point P? 200,000. 200,000 times 10 to the 3 squared. And then you want to do the gravitational field strength for the point P using capital G, but the mass of the Moon. And then that distance is only 100,000 times 10 to the 3 squared. And we can calculate these. I'll let you guys do them as well. You can use your data sheet. I want you to get into the habit of doing that. So find your data sheet. Go to the back of the data sheet. Oh, it's on the screen too. Confirms what I got. So I didn't use the radius of the Moon or anything because it looks like it's given me the radius plus the distance. So I didn't use radius of Moon, and I didn't use radius of Earth. The first one I got like 0.009. 9. Okay, 7, 1, sure. And then the second one I got like 4.9 times 10 to the negative 4. Do you guys also get that? Okay. This brings up a pretty interesting idea here. Let's just think about it for a second. Which way does the first calculation, the 0.009 point, which way does that point? Left, and the other one points to the right. So when you put those together, GP1 plus GP2, I'll attach a negative to the 0.009, and then I'll plus this 4.9 times 10 to the negative 4. It looks like we're probably going to get 0 here. We essentially get 0. 0.009 negative. I mean, it's essentially 0. Do you think that's possible? Just think about it for a second. Is there a point in space between the Earth and the Moon where the gravitational field strengths actually kind of cancel out? Is that possible? I think that might be okay. The Earth is pulling you left. The Moon is pulling you right. The Earth is way more massive, so you have to be much farther from the Earth for this to happen. And I guess if you were placed right there, some super powerful being just dropped you right there, you wouldn't go anywhere. You'd be stuck at rest forever. Maybe some gravitational or some galaxy wind maybe come across. I don't know. Give you a little push. But I think you're stuck there for eternity. Anyways, this is the homework.